All right, so this is going to be chemical kinetics. So we're getting into the real stuff. Last time we went over some Chem 50 information and material that hopefully would have been helpful to you. Once again, you could find some more review topics of some of that Chem 50 stuff up on our Canvas site in the module towards the top there. And again, as we talked about, really important in this class to understand first off, really solutions, molarity, concentration, dilutions. Second to that is really the ability to be able to take words and really turn them into balanced equations so you could understand what is happening. Those two things are really crucial to being able to sort of succeed in here, along with other things like obviously figuring out, kind of like lab today, you know, how many grams there are and stuff like that, using molarity and molar mass and things like that. But the two really big things that people truly struggle with is the just cannot write an equation to save themselves no matter what happens. And people really think, well, is it really that important? And it really is for the conceptual understanding of what's going on in these chapters, and really the whole solution and molarity. You know, it's a struggle for a lot of people. So, you know, make sure if it is an issue for you that you kind of maybe take some time, go back and, you know, do some review problems, maybe look at those review sheets and stuff like that, so that you're hopefully in a good shape. And you could always come ask me as well. I'll still tell you how to do it. I'll help you through it, I guess is a better way of saying that. I won't do it for you, but I'll kind of walk you or help you through it if you need help. All right, so we're going to start with chemical kinetics, which is a slightly different topic than a majority or the chunk of the information that we do in this class, which is equilibrium. But it does tie into a couple of things. So chemical kinetics really is the study of the rate of a reaction. And there's really kind of two areas that we look at a lot of times in chemistry. And one is thermodynamics. And thermodynamics you might have touched upon, I hope you touched upon in Chem 50. It's like energy, for example. Law of conservation of energy is the first law of thermodynamics, right? All that delta H's, Hess's law, everybody's favorite stuff, right? All that kind of stuff. You know, so that is an important part of sort of thermodynamics. In this class, we will talk about some other parts of thermodynamics, which is things like entropy and disorder in sort of the universe. And we'll also talk about Gibbs free energy, which is energy that's available to do some type of work, which is the other parts of sort of thermodynamics. But really, as sort of a broad category, thermodynamics really deals with the idea of, you know, whether or not a reaction takes place. So oftentimes when we think about thermodynamics, and we will hit that after we get through most of the equilibrium stuff, we think about thermodynamics, we usually ask the question, you know, is this reaction spontaneous or is this reaction non-spontaneous? And sometimes people have a very wrong understanding of the word spontaneous, because sometimes when we think of spontaneous, we think of it must occur super fast, right? It's like spontaneous, boom, it's going to occur. But really in the sort of category of thermodynamics, as we will talk about it, as you talk about it before, spontaneity really just means whether or not that reaction will take place. It could take place really fast. It could take place super slow. But what spontaneity means in the term of thermodynamics is under those particular conditions, we would expect this reaction to take place, again, very fast or maybe very slow. When we're interested in whether or not or how fast, or I guess another way, how slow maybe a reaction would take place, that is really what kinetics is about. So what this chapter is about is really that, how fast or slow a reaction takes place. So the focus of this chapter is on that and the kinetics of reactions. So a lot of times when we talk about how fast or slow something takes place, we oftentimes deal with what is sometimes referred to as the reaction rate. The reaction rate in terms of what we would be interested in a lot of times is how is the concentration of a reactant, maybe a product, changing over a period of time. And that is why the units typically of reaction rates are molarity over seconds. Molarity obviously is, as we talked about the other day, are moles per liter, right? And it is a concentration, right? So basically when we see something like this, which is molarity per seconds, it is telling us how the concentration is changing over a period of time, which is basically what a rate is, right? A rate is how fast you're going over some period of time, like how fast you drive your car and so forth. When we look at a reaction such as this one here, A goes to B, we could actually write what is sometimes referred to as the rate expressions. And the rate expressions are these kind of guys right here. And in this case, we could say that the rate is equal to negative the change in the concentration of A over the change in time. A reminder that when you see these little brackets, they do mean concentration. Thank you. And typically, for the most part, we're talking about molarity in terms of the type of concentration that we're talking about. The delta means change. And we could also write one for B, which is a product, right? And we could say the change in concentration of B over the change in time. We do see a little bit of difference here in terms of this guy here has a negative and the one below it does not have a negative. And the reason for that is as this reaction takes place, the reaction is going from A, right, which is, I know we all know this, right? Again, our reactants, right? On this side is our products. Right? So as A goes, it will start to form our products on the other side. In order to form our products, we need to use up some A, right? So the amount of A over time should be increasing or decreasing. The amount of A should be decreasing with time, right? So the only way you can make your products is to use up your reactants. So the amount of A should be dropping over time. With that same token, the amount of B, which is the product, should be making over time or increasing over time is a better way of saying that. So we should see an increase in the amount of products as this reaction takes place. So because the amount of reactants are decreasing with time, we represent that in the rate expression with a negative sign there in front of the rate expression. And the reason for that is, typically speaking, when you calculate the reaction rates in either of these things, it should be a positive number. So if you just think about the reaction of A going to B, and let's just say we started with 4 molar of A and we ended at the end of the reaction with, say, 2 molar of A. If I wanted to calculate the change in the concentration of A, I should take the final concentration, right, minus the initial concentration. So if I did that and took the change in the concentration of A, in my example there, it would actually be 2 molar minus 4 molar, which gives us a negative 2 molar, which means that this number in here will be a negative, and with the negative on the outside, that is going to turn my rate into a positive number, which is what it should be. That is different than B, for example, right? B, say, started at 0 and ends at 4 molar. That means when I do the change in the concentration of B, it is 4 minus 0, which gives me a positive 4 molar, which means this guy's positive, no need for negative to make it negative, and that gives us, again, a positive rate. So that change in the concentration value will either be positive if it is a product, because it should be increasing with time. You always should have more product than what you started with. And the change in the concentration of the reactant should always be less, because you should have less reactants than what you started with, because that, again, is the only way to make products. Any questions on that there? Now, obviously in kinetics, there is a lot of graphs and visual representations of sort of what's going on. So here's just a visual representation. Clearly, when the reaction starts over here, this would be like time 0. We basically have all black circles, which represent A. And as time sort of progresses to the right, we see the disappearance of our reactant circles and our product circles start to appear, our red circles. And as we get closer and towards sort of the end of the reaction, we obviously have a lot more products than we started with, and obviously a lot less reactants than we actually started with as well. Graphically on the bottom, that's also what we see at time 0. It is all reactants. no products. And as the reaction is progressing, we see a decrease in our reactants, but we do see an increase, obviously, in the amount of products that are being made. One thing about the kinetics chapter is they love graphs, they love tables. There's a lot of graphs and tables that you see a lot in kinetics chapters. Now, an experiment like we are going to do, and I sort of described it a little bit earlier, this is sort of like an experiment where I was talking about where you kind of mix the two beakers together, it kind of turns a color, reaction proceeds, and then it basically ends up with no color at the end. So this is sort of the progression of what we're seeing. And as we talked about today, using something like Beer's law, we can follow the absorbances over time. And like I mentioned, we could do sort of a Beer's law graph and convert our absorbance values into concentration values. And just by actually following the absorbance of a solution over a period of time, we can actually figure out sort of the rate of what's happening in that particular reaction. On the left-hand side, we see the darker color, which is pretty much the bromine here, which is causing that color. Everybody on this side of the equation is pretty much colorless. So we could visually see as this reaction progresses, we're really making more products, right? Because the color is getting lighter and lighter. Also means we have less of the reactant molecules there, right? As Y is getting lighter and lighter till the reaction is really complete. We talked earlier as well that we would pick obviously a light source with a wavelength, and this is a similar graph to like you would see. Again, we would want to pick that peak absorbance that's going to allow all of your samples really, or the wavelength where you see the peak absorbance, it's going to allow all your samples really to be red. In the case of these beakers here, which beaker, the one on the left, the one on the right, has the greatest absorbance? The one on the left, right? It is the darker color. It should absorb more of the light. Obviously, the one on the right probably will start giving you 0 readings, maybe some negative readings there at the end there. And you know for sure your reaction is done. If you were following sort of the absorbance, for example, over time, what you would see is if it's sort of a linear relationship, you would see it decreasing, right, with time. And eventually it will flatline, right, the absorbance. And that's sort of where you know the reaction is done. And that's sort of what your graphs, when we get to the kinetics experiment, should actually look like. But the timing aspect of it, as we talked about in lab earlier today, if you take too long, you miss this entire part of the graph and you catch just this part, which it looks like just a flat line, which doesn't give you much absorbance values or anything like that to do it. So ideally, you know, that's sort of what your kinetics graph should look like when we get there to that experiment. So you do want to be efficient, as we talked about. Otherwise, you'll just grab the back end of it when the reaction is pretty much done at that particular case. Any questions on that there? Now, when we talk about rates, there's a couple of different sort of rates that we sometimes refer to. And if we graph it again, you can see here, this is this reaction. And over time, we have the concentration of Br2 starting to decrease. You can take the slope of the tangent of the line to figure out sort of the instantaneous rate over a period of time. But there is kind of 2 rates. One is an average rate, which is basically the change in the concentration of Br2 over really the whole run, if you will, kind of final minus initial and divided obviously by final minus initial time. And there's also an instantaneous rate, which is really just for a specific period of time. So I kind of relate the differences between the two like this. If you were driving, say, from here to Arizona, which I don't think you could do after last night because the freeway got washed away. But say the freeway was fixed at some point and you're able to drive there. Anybody see that? The like 10 freeway got washed away like by Blythe from thunderstorms. The entire freeway, a section of it's gone. People were stuck in there for like hours. Like they had nowhere to go. They had a lot of flash floods last night. So apparently if you're heading that way, by the way, on the 10 East, closed down there heading towards Arizona. Don't head that way. You have to go all the way around the 40, I think, and all the way back down. But so if the freeway was open, you're driving here to Arizona, for example, at that point in that drive, if you ever done that drive, it's like 65 is here, right? Then it goes to 70 out in the desert, 75 when you get into Arizona. So along that journey there, maybe, you know, there's pockets where maybe you're doing 65, 70, 75, 80, 85, not more than that, I don't know. So, there could be an instantaneous part of your trip, right, where perhaps you're going at a much higher rate or a much slower rate than it would be if you took your entire journey from like your home to when you arrived there. On an average, maybe you only did about 70 miles per hour on the average trip, but there were pockets there of instantaneous parts where for a short period of time, maybe you were moving faster, or a short period of time you were moving slower. So that's sort of the idea between an instantaneous rate and sort of the average rate. A lot of times we look at the average rate over the whole entire reaction, but for different pockets of sort of the reaction as it's progressing, it could progress a little faster or a little slower than, say, the average sort of speed over the entire haul. So in case you had those travel plans for this weekend, don't do them. I had those travel plans for this weekend. Sad. All right. So we can look at the relationship in a reaction like this. And this is a table of the bromine and the rate. And that's sort of the instantaneous rate at different sort of periods of time. And we do see that there's a wide variety of sort of rate values that we get there. But there actually is sort of a consistent value that we do see in these type of reactions, and that is sort of this column right here, and that is the little k here. And I write it little k. This is the rate constant. It sort of gives you an idea how fast the reaction is taking place. The reason it's little k is because after this chapter we go to large K or big K, and that is the equilibrium constant. And they are different things, by the way. So if you are expressing the rate constant like you should in this chapter, it should be lowercase k. If you're doing pretty much every other chapter outside of this, which is equilibrium, it should be capital K. So what we're dealing with here is the lowercase k, which is the rate constant, how fast it sort of occurs. You can, and we'll talk a little bit more about this in this chapter as we go through, but this is what is sometimes referred to as a rate law. And that is the rate is equal to the rate constant times the concentration of the reactant there. And if we rearrange this rate law and solve for K, we get the rate constant, which in this case has units of reciprocal seconds. And the way we get that is typically the rate is molarity per second divided by the concentration, which is molarity. Those guys cancel, gives you 1/seconds or reciprocal seconds. One really important thing about the rate constant, in addition to, if you have a really large value for the rate constant, it means the reaction proceeds very quickly. If you have sort of a smaller value for the rate constant, it proceeds a little bit slower. But the other thing that's really helpful about the rate constant is actually the units that you see associated with the rate constant. The units associated with the rate constant will actually tell you what type of reaction you're dealing with in terms of, is it a first order reaction, a second order reaction, a zero order reaction? And we'll talk about what those are in a bit here in this chapter. But it gives you a really good understanding of what type of overall reaction you're dealing with. Now, that's really important because in a kinetics chapter, they oftentimes, when you get to certain types of problems, you need to use specific formulas depending on whether it's like a first order reaction, second order reaction, zero order reaction. And a lot of times they won't just come straight out and tell you, hey, this is a first order reaction with blinking lights. They will give you the value of the rate constant with the units, and they assume that when you see the units there with the rate constant, you'll know, oh, this is like a first order reaction, or this is a second order reaction. So as we go through this chapter, you should keep in mind the sort of common units that you see associated with the rate constant, because it can be very helpful in you choosing sort of the right formulas as we go through. By the way, something with 1/seconds or reciprocal seconds, or really reciprocal time, is typical of what is referred to as a first order reaction, which is typically like one reactant, maybe two reactants that are reacting in a particular reaction. Now, using something like a spectrometer, like we talked about in lab and we saw on the previous slide, is really helpful, especially when you have some type of solution that makes a color, be it a solution that the reactants have color or even products have color. So you can start by mixing and there's no color, and then slowly, right, a color could sort of develop And that also is a way that you could do a kinetics experiment. Popular experiment kind of like that is like the iodine clock. You know, you mix it together, put some starch in, you wait and you wait, and eventually the solution turns blue. Anybody ever do those experiments? Yeah. 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 So usually you're sitting there with a stopwatch and you're like, is it going to turn blue? It's never going to turn blue, right? And as soon as you look away, it turns blue, right? As soon as you're at that moment, it turns blue. So that's another way you could obviously use something like spectrometer if, you know, again, if you have a product that does that. But what if you do have a reaction, say like this reaction here, where, you know, everything is sort of colorless. If everything is colorless, could you use something like a Spec 20, a spectrometer? Is that useful if everything's colorless? Can you do a reaction like that? Right. You can't really do that, right? Because if there's nothing that has color in the reaction, you could put it in that little cuvette in there. You'll never get absorbance, right? Everything's going to be zero. So that's the advantage of using something like that, where you can follow absorbance when you do have something that has color. But obviously, if you have nothing that has color, probably like a post-lab question in that kinetics experiment, by the way. If you have something with no color, you obviously it's useless to you because there's going to be no absorbance. There's no way to follow what's going on. So something like this where we wouldn't have color, obviously everything here is colorless. But what we do have is actually a gas being generated here. So this is a gas, right? That's oxygen gas being generated here. And when we think about gases, we think about our good friend, the ideal gas law. Yeah, that is PV equals nRT. By the way, here, the pressure should be in what units if you use the ideal gas law? It should be ATM. Volume should be liters. N is moles. Yeah. T is Kelvin. Yeah. Temperature. R is the gas constant, right? R is the 0.08206 liters atmosphere Kelvin mole, right? All right. Now, when you have the ideal gas law here, obviously gases generate pressure, which is what we're looking at here, right? Kind of closed system. As the gas generates, it goes through the tube. It's got nowhere to go, creates the pressure in the tube. And you can measure the pressure by the height of the column of the mercury and all that good stuff that's in the tube. Now, in this particular case, if we take the ideal gas law, which is PV equals nRT, and we solve for N over V, which would be P over RT. N is moles, right? V is volume, which is liters. That is moles per liter, which is also known as molarity, right? So you could actually figure out the concentration of a gas by using the ideal gas law and solving for N over V, which is moles per liter, or the molarity of a gas. Though we don't really think about molarity a lot of times with gases, but you can actually do that and figure out the concentration. The advantage of that is if we look at what is left of the ideal gas law, we have P over RT, right? R is obviously a constant, which means it's not going to change. If you did this experiment, there's a pretty good chance the temperature is going to stay the same. You're in the same room. It's probably not changing either, which means for the most part, these guys here are constants. That means really the only thing that you would need to monitor in this type of experiment would be the change in pressure. And by monitoring the change in pressure in this sort of experiment, you would be able to figure out really by using some calculations how the molarity of that gas is basically changing over time. And that's what it shows here by looking at the change in pressure over the change in time. You basically can back sort of calculate it, if you will, and figure out basically how the concentration of O2 over time is changing. The reason we could be very confident here is the only gas that we see is oxygen, right? So the only way that we could get pressure is to produce what? You would have to produce the oxygen, right? In order to produce the oxygen, that would mean the reaction had to happen and we had to make some products, right? So that's how we know this reaction took place. It happened. When this reaction would start, we would pretty much have no pressure, right? And as this reaction progresses, as we start making more oxygen, we would start to see a rise in the pressure, and that tells us we're making more products in this case. And by default, we would obviously be making more water in that case. So as an analogy, that it should be coming along for the ride. Any questions on that there? All right. So let's talk a little bit about reaction rates, though, and everybody's other favorite thing, which is stoichiometry. We cannot forget our multiple relationship, as we talked about. So when we do look at this reaction here, 2A goes to B. Stoichiometry rise, that means that for every 2 moles of A you throw in there, right, you get 1 mole of B out. And that is nothing more than the coefficients, right? In the balanced equation is where those come from. So when we take into account how the reaction is changing over time and the rate of how it is changing, either reactants or products, when we write a rate expression, we do need to take the stoichiometry into account to get sort of the right correlation that's happening. So the way we do that, where you could kind of take into account both the stoichiometry and the rate and the reaction and the kinetics together, is you basically take 1 over the coefficient. So the coefficient here for A is 2. So that is why it is negative, because it's a reactant. 1 over the coefficient, which is 2, the change in the concentration of A over the change in time. When we get to B, the coefficient basically is 1, which is 1 over 1, which is 1, which gives us the change in concentration of B over change in time. So again, technically speaking, is 1 over 1, which obviously equals 1, which is why it wasn't put in there to begin with. It is positive, like we talked about previously, because again, the amount of product should be increasing with time. And again, we have our negative sign over there for our reactant, because again, we want to make sure that this guy ends up as a positive number. In general, if you have a reaction like on the bottom there, AA plus BB goes to CC and DD, you could do that for everybody in the equation. The nice thing about this is, as you can see there, you pretty much could set everybody equal to each other, or you could individually take each piece out like they did above and go, the rate is equal to minus 1 over A, the change in A over the change in time. The rate is equal to 1 over C, the change in concentration of C over the change in time. This rate value here and this rate value here, they are the same number. So that is why you can set them equal to each other. That's why it's very useful. You can pull out whatever parts of the equation that you're interested in and kind of do them separately, and then relate them to each other through that rate value that you see there. Now, you can, if you want, because it really is stoichiometry, if you wanted to, you could do like the stoichiometry part first, like a traditional mole to mole sort of calculation, and then do the kinetics part. Or if you do it like this, it will kind of do both of those things together for you in kind of one move. Any questions on that? So what this allows you to do is, if you know really just one piece of information about that actual reaction that's taking place, maybe you know how a reactant is changing with time, or maybe you know how a product is being made with versus time, or maybe you just know the average overall rate, you can figure out pretty much how everybody in that reaction will change with time by using these rate expressions, which is what this basically is a rate expression. Any questions on that? Okay, why don't you take a sec here and write the rate expressions here for this reaction. Okay, let's take a look here. So we could say in this case, by the way, what type of reaction is this? It is a combustion reaction, right? It's an organic combustion reaction. That's methane plus some oxygen, a little carbon dioxide and water there, some flame. That's like your Bunsen burner action. So here we could do the rate is equal to, we'll start with our reactants. So because our reactants are decreasing with time, we do want to put the negative 1 over the coefficient. So for CH4, the coefficient is 1, so we don't really need to put it. And then this would be the change in the concentration of CH4 over the change in time. If you want to set the next one equal to that, you can. And again, here we have O2, which is a reactant, so it should be negative 1 over the coefficient. And once again, that takes care of the mole-to-mole relationship, and that's really why we're doing it. The change in the concentration of O2 over the change in time equals, now we've moved over to our product size, so those should be increasing with time. That would get us positive, and then once again, the coefficient here is 1, so we don't really need to put it to change concentration of CO2 over the change in time. And here we have the coefficient of 2. Once again, it will be positive because it's a product. 1 over 2 for stoichiometry, change in concentration of H2O over the change in time. I wrote them all together. You could individually for each one separately write the rate is equal to whichever part that you got there, and you could do it either way there. Any questions on that there? Where's the this part? Yeah, so the general way that you do it to do the stoichiometry part of it is you take 1 over the coefficient from the balanced equation. So the coefficient for CH4 is actually 1. So technically it's 1 over 1, which is 1. So usually we don't include 1 because it's not necessary, which is why there's nothing here. Now when we get to here, it's 2. So we take 1 over 2, and that's where that comes from. Yeah. Other questions? All right, so why don't you try one here? Why don't you try one with actually some numbers, do a little calculation and see. So let's say that for a reaction, the concentration of I minus changes from 1 molar to 0.868 molar in 10 seconds. Calculate the average rate and for the first 10 seconds, and what would the concentration of H plus over the change in time be? I don't know if your handout has this part of it, but this is what we're looking for basically there. All right, so take a moment or two, see what you come up with. Minus changes from 1 molar to 0.868 basically in 10 seconds. We're looking for the average rate and basically how the concentration of H plus is changing over time. So really, you could do it a couple of ways, but one way you might just want to sort of isolate the two things, obviously, that you are maybe interested in. Obviously, they did give us the I minus, so we could go to the equation and write our rate expression for the I minus, which would be the rate is equal to minus 1 over 3. Again, it'll be minus because it's a reactant, 1 over the coefficient, which is a 3. And that would be the change in the concentration of I minus over change in time. Obviously, eventually at the end here, we do want to get to this guy, which is the H plus, which we also could write the rate expression, which is the rate is equal to, it is also a reactant. So it would be minus 1 over 2 change in the concentration of H plus over the change in time. So now that we have our sort of rate expressions, really all the information that we have is for I minus. So that's where we want to start. So we could start with that. We could just basically fill in the numbers here. So the rate is equal to minus 1 over 3. Now the change in the concentration of I, again, is final minus initial, and this is important for the sign that you end up with. So you should be taking 0.868 minus 1 molar here. Again, that is final minus initial. And that would then be, although they didn't tell us the initial, the first 10 seconds would imply that the initial is 0, right? And the final would be 10. So this would be 10 minus 0 seconds in this case. Any questions on that? Again, this is important because this top part here is going to give us a negative, along with this negative, as we talked about, will turn our rate into a positive number, which is what we are looking for in this case. So that would be 0.868 minus 1 divided by 10 divided by 3. That is going to give us 0.0044. The units here are molarity per second. Yes, so molarity up on top, seconds on the bottom. That would be our average rate for this reaction. On average, everybody is changing by 0.0044 molarity every second as this reaction progresses. That's basically what that means, yeah. on average, that's what everybody on average is changing. Again, not instantaneously at a particular period of time, but over the long haul of that, that is basically what it is changing. The second part that we're looking for, though, now is the concentration of H plus over time, right? That's what we're looking for. So if we look at our sort of rate expression for the H plus, the rate is equal to -1/2, change in the concentration of H plus over the change in time. We are essentially looking for that part, which means the only thing we really need is the rate. And where can I find the rate? I just solve for it right here, right? So that is the same rate. So that would mean that we would have 0.0044 molar seconds is equal to -1/2 change in the concentration of H plus over the change in time. To solve for that, we need to do what with the 2? We need to multiply it to the other side, but not just the 2. We also need to take the negative with it, right? So we got to multiply the -2 to the other side. And that would give us 2 times 0.0044 with the negative would tell us that the change in the concentration of H plus over the change in time is negative 0.0088 molar seconds. Now, does that make sense for the H plus in terms of its sign? It does, because H plus is a reactant, which means it should be decreasing with time, which means the rate at which it's coming down should be represented by the negative. It's dropping basically 0.0088 molarity every second. So the H plus part of it is losing that much concentration every second, represented by the negative sign. As opposed to overall, and you can see here overall, right now it is doing about twice as much change as everybody overall, right? Everybody overall is changing 0.0044 molarity per second. H plus is cranking out at about 0.0088, right? So again, sort of that, you know, things can be moving faster than other things, right? And it's based on the coefficient and the multiple relationship of how much is reacting, right? Because basically, as compared to peroxide, for every 1 peroxide you throw in there, you got to double the amount, right, of H plus you got to throw in there with it. And that's why we see more of it changing over a period of time. Any questions on any part of that calculation there? So why don't we try here another one here. If 2.4 times 10 to the 2 grams of NOBr, that is the molar mass there. That is grams per mole from the periodic table. I'll throw the moles in there for free. Decomposes in a 2 times 10 to the 2 milliliter flask in 5 minutes. Calculate the average rate of Br2 production in molarity per second. So see what you come up with here. Okay, let's take a look and see how we're going. So once again, if you want to take the approach, we can kind of pull out the 2 sort of rate expressions that we're probably going to use here. Obviously, one would be for NOBr there, which would be the rate is equal to -1/2. Once again, NOBr being a reactant, so the negative 1 over the coefficient takes care of the stoichiometry, change in our concentration over the change in time. We're also interested in our Br2, which is over here. So that would be the rate is equal to 1/1 because the coefficient is 1. Change in concentration of Br2 over change in time. At this point, we do need the change in concentration. So we do have to actually calculate the concentration here, which is moles per liter. We do have grams, and we do have the molar mass from the periodic table, which is where that number comes from. And we do have the volume. So our volume here is basically 200 milliliters, which is basically 0.2 liters, because we do need to convert it to liters, right, to calculate molarity. Molarity obviously would be moles per liter, so we also need to calculate the moles. So the moles here would be 2.4 times 10 to the 2 grams. I don't know why they didn't write 240, but all right, divided by 109.91 grams per mole, doing a little dimensional analysis like you should be showing the work. 2.4 to the 2 divided by 109.91 gets us a 2.1836 moles of NOBR, which we then can divide by the 0.2 liters, which is our volume. And that would get us a molarity here of, call it 10.9, we'll call it 2 molar NOBR. Any question on that calculation there? At this point, that basically is what goes into here. So we could put in there that the rate is equal to -1/2. Our change in concentration is basically negative 10.92 molar divided by our time, which is 5 minutes. Since we're looking for seconds at the end, I might want to do a conversion of my 5 minutes into seconds. A minute is 60 seconds, gives us 300 seconds. Gives us 300 seconds down there. Why did I put a negative here? It is a reactant, so if we technically did the final minus initial, it would give us a negative number, and we would expect it to be negative. And again, if we didn't put the negative there, we're going to end up with a negative average rate, which we don't want, right? So in this case, that's why we want to make sure we put that negative in there. So if I do all that there, and that again is for our NOBR, we will get, I think, divided by maybe a 2. Yes, 10.92 divided by 300. There you go. Divided by 2. Gets us a rate of 0.0182. And because I got my units all good there, I got molarity per second. Now we could use this to relate it to the BR2, and we see from our first little spot there that the rate is equal to the change in concentration of BR2 over the change in time. And since this is the rate, that would also be the answer for that, because it basically would just go right there, right? So it's basically the same number. So our BR2 over time is actually increasing the exact same rate as the average rate for the overall reaction. And again, every second it is gaining 0.0182 molarity. Basically every second is picking up that. Question on any part of that there? Now, as we did it here with 1 over the coefficients, it does take into account the sort of stoichiometry and kind of does the kinetics part of it all together. Just to show you, if you wanted to sort of treat it more like a stoichiometry problem first, and then sort of go into the kinetics, you could. So for example, you could take the moles that you got here and do 2.1836 moles of NOBR, and then just do a basic stoichiometry problem. 2 moles of NOBR is 1 mole of BR2, and that would then get you 1.0918 moles of BR2, which at that point you then could divide by the 0.2 liters. That gets you the molarity basically of the BR2, which then you can divide by the 300 seconds, which would then get you to the molarity per second and back to here as well. So you could do it as sort of a stoichiometry problem and then roll it to the kinetics part of it, or you could just do 1 over the coefficient and it kind of bundles it all together in sort of one calculation. Any questions on any of that there? Yeah. Can I explain, say what? So the reason if your question is why we kind of focused on NOBR is really because that was the only really information that was given to us. So what was given to us was the grams of NOBR. We also had obviously the volume and all that kind of stuff. So one approach was how we did at the beginning there. Since we have everything about NOBR, we basically could use the rate expression for NOBR to figure out the average rate of the reaction, which is what that 0.0182 number represents. And then at that point, much like we did before, we could then use the rate expression for the BR2 to figure out how it's changing with time. And in this particular case, because there's coefficients are all ones and there's nothing there, it basically means that it's changing basically exactly how the average rate's changing. So once we found that, that really was how that guy was changing as well. The reason why we had a different number on the previous problem was the stoichiometry in the previous problem was like a 2, I think it was. So we had 1/2. So we had to adjust it for the mole-to-mole relationship in that one. But in this case, basically, this guy will be changing exactly how everybody averagely is changing over time. Other questions? Yeah. There. It really should be. I kind of biffed that, but it really definitely should be 2 significant figures. So it really should be 0.018 is what it really should be. Thank you. The magic of erasers. Let me do that right. Let me make it up right. But you're absolutely right. And this one, pretty much everything was 2, so it should end up as 2. Yeah. And it's a good reminder that you should obviously get the right number of significant figures, and also a good reminder as well that make sure you don't really round too much though until the very end, because you don't want to go too much rounding, move far away from the answers. Other questions? All right, so let's talk a little bit about factors that do affect the reaction rates. And some of these will go into a little bit more detail as we continue through this chapter. But the nature of the reactants, meaning sort of what physical state they're in, can also play a big effect at whether or not a reaction may proceed fast or may proceed slowly. Typically, smaller molecules do tend to react faster than larger molecules. Gases do react faster than liquids. And if you think about it, what are gases doing? They're pretty much flying around with lots of energy, right? And for things to react, there's really, as we'll talk about, 2 things that's got to occur. There's got to be some type of collision between things to allow the reaction to take place. And they actually do need to hit each other in the right spot with the right amount of energy. So obviously things in the gas state have a lot of energy, so they're flying around. So they, in most cases, can pretty much accomplish all that just by the nature of them flying around. Obviously, liquids will react faster than solids. Solids, frankly, are just kind of sitting there, right? They need some help. They're solids, they're not moving around, so they don't react very well without a little bit of help. But even the solids can react, and powdered solids do react more reacted than, say, block solids, and that's really just more surface area for reactions to take place, right? If you kind of spread everything out, it reacts really well. If there's just a small availability of it, it doesn't react really well. Maybe in Chem 50, do they do the one with the magnesium where you wrap it up in a coil and you react it with hydrochloric acid to produce that, right? If you ever did that reaction, and maybe this happened to you, if you took your magnesium and you were like super like, I'm going to coil that thing into a tight ball, right? And you did your reaction, you're like, I got like no bubbles. I got like a little bit of bubbles, but I don't have a lot. And that's because you pretty much hit all the magnesium, right? And the hydrochloric acid had a very hard time trying to get into your nicely coiled thing. There's usually 2 things that happen. You coil really too tight, or the person that ties the string doesn't tie it very well, right? And off goes your magnesium that floats right by the hydrochloric acid as they pass in the night. The hydrochloric goes this way, magnesium goes that way. You don't get anything. But if you kind of loosely coiled it, the purpose of that is it allows obviously a lot more surface area for the HCl to get to and start that reaction. I've seen that in a worst case scenario, like everybody around this poor group is cleaning up and they're still waiting for like one blob. They actually restarted and finished faster than the first one. There was still like blobbing one little bubble at a time. So certain chemicals are more reactive than others. Activity series of metals, like when you talked probably about single replacement reactions, right? In single replacement reactions, for example, whatever is coming in, like the zinc and the magnesium and the hydrochloric acid, needs to be more reactive than what it's replacing. And that's why we do get that reaction, kind of like we talked about earlier this morning with the pennies. Copper is less reactive than hydrogen, so we don't get that reaction that takes place, which is why the old penny never really dissolved in the hydrochloric acid. Ions are definitely more reactive than molecules because, frankly, where's the one place where we see ions? Where do ions really are in like a real life situation? Where do we find them? Anybody know? What state are ions in typically? Solid, liquid, gas, aqueous. They are aqueous. Ions are typically found in solutions, right? And they're aqueous in solutions, which means they're floating around ready to go, right? Which is why when you have a solution and you add something to it, say like some silver nitrates of sodium chloride, the sodium ions that now started floating around can find the chloride ions really quickly, and you make the white silver chloride solid, which is a common reaction that you do a lot. So ions, because they're typically in solution, they're floating around, they're good to go. You know, they react a lot faster than molecules where you might have to break some bonds and stuff like that. When you have molecules, right? Molecules are held together to other molecules through what type of things? They're held together through intermolecular forces, right? Like dipole, hydrogen bonding, little dispersion forces, right? So you have none of those things you got to kind of break apart like you do with molecules. Ions don't really have those things. Temperature is a really big factor in terms of how fast or slow a reaction takes place. Generally speaking, if you increase the temperature, the reaction should occur a lot faster for most reactions. And if you decrease the temperature, it should occur a lot slower. And if you raise the temperature about 10 degrees Celsius, you typically will see a lot of times the reaction sort of double its rate as well. Like the old saying, if you light a fire underneath somebody, they move a little quicker, right? So it's the same idea when you do that. Why is that the case? It is because of what I mentioned earlier. Pretty much for a reaction to occur, you got to have a collision, you got to have the right amount of energy. So clearly, if the temperature is raised, you have a greater proportion of molecules that have sufficient amount of energy basically to get the reaction going. And when those collisions occur, they're able to really take off. The opposite is true if you decide to throw everything on ice. You're basically going to remove a lot of energy from that system, which means you're going to have a much smaller proportion of molecules that have enough energy to really get the reaction to take place. So that's really the opposite effect of that. And there's actually an equation that we'll see, which is known as the Uranus equation, where you could calculate that, the effect of changing the temperature on the reaction rates. And we'll talk about that a little bit later on. Another very common way that reaction rates are changed or that affect reaction rates are catalysts. And once again, catalysts are not reactants and they are not products. And they, once again, do not get used up in the chemical reaction. They are really there to facilitate the reaction, in most cases, to facilitate it occurring faster. There actually are catalysts that slow down reactions, but most of the time when people talk about catalysts, they do talk about it in the sense of it speeding up the chemical reaction. And they could do it in one of two ways, several different ways, but a lot of times, if you have, for example, like a solid catalyst, what it sometimes will do is provide an area where everybody's sort of attracted to, right? So what that does is get everybody in sort of a central location that allows that reaction really to sort of take place a lot more efficiently than if that wasn't there and they're just flying around trying to find each other. So it kind of puts everybody in a very central location. Sometimes could even help with the breaking of the bonds and kind of making of the new bonds, the catalyst as well. Catalyst could be homogeneous, which means that the catalyst and whatever is reacting are in the same phase, right? Homogeneous mixtures means everything's the same throughout, right? And that's what the homogeneous catalyst means. A heterogeneous catalyst means that the catalyst and whatever's reacting are in different phases. So maybe again, your reactants are gases, and maybe your catalyst there is a solid. Typically, a lot of times we will see catalyst written on top of the arrow. So you'll have maybe something like H plus, which means it's like an acid as a catalyst. Sometimes it may be a base. A lot of times some type of solid like platinum is up there or something like that. And again, these things are there to facilitate the reaction occurring faster. How does it do that? And we'll talk a little bit more about it later, but basically it's able to lower what's known as the activation energy. So it's really able to, by making the reaction more efficient, lower sort of the energy demand on the reactants. And by doing so, what that does is it allows a greater proportion of molecules to be able to go, cool, now I have enough energy to get over that kind of smaller hill to the other side. And thus it usually will speed up the reaction. Any questions on that? Now, the concentration is really important as well. The larger the concentration of the reactant molecules, typically the faster it occurs. We've talked about molarity a couple of times today, but really, what is the true definition of molarity? It is the moles of what? Anybody know? It is the moles of the solute, right? Divided by the liters of solution. Right? When we talk about a solution, as you may know, or if you don't know, let me tell you, it is made up of two things, right? It is, again, the solute, which is the smaller part, and it is the solvent, which is the larger part. The thing that is truly reacting when you pour two solutions together, is it the solute or the solvent? What is really the thing there that's reacting? It is actually the solute that's reacting, right? So it's actually the smallest thing that's there dissolved in the solution. Because let's be honest, solvent in a lot of cases is water, not always, but a lot of times it's water. So it's not really the water reacting. It's actually what you dissolved in the water. The water is sort of the vessel at which allows those ions to float around, for example, and be able to react. So it's really the solute that reacts. And that's why when we do a dilution, as we talked about, I think the other day, the moles of the solute before dilution, the moles of the solute after the dilution are the same. And we're just adding more solvent. So whenever you do any type of reaction or any type of sort of combination, when you pour solutions together, it is really only the amount of solute that you have in there as to how much reaction you could get. So if you have a large concentration, the only way that we could get a large number for M would be that this top number would also need to be a large number, right? So if it's a large number, that means you have a lot of solute in that solution, and thus you have a lot of things floating around ready to react a lot faster than if you had a lower concentration. That would mean you would have a much smaller number of solute molecules in there, and thus we would have a little slower time of everybody reacting. So again, with those large concentration, it really does increase the frequency at which those reactant molecules could come together and react. Concentration of gases depends on partial pressures. At higher pressures, we also have a higher concentration. Pressure and volume are also related to each other. What happens when you have high pressure? What type of volume do you have when you have gases? You have a small volume, right? They're inversely proportional to each other. One goes up, one goes down. So if you have a high pressure, that would also imply that you have a small volume, which means if your gas molecules are now in a much smaller volume, they are much closer to one another, which thus would allow them to react a lot faster than you had a lower pressure where the volume would be a little bit larger. So they got to fly around and find each other a little bit longer time to do that. And you would expect perhaps a little slower rate. Any questions on any of that there? All right. So let's talk a little bit about the rate law. The rate law is a little bit different than the rate expression. So the rate expression is typically used when we're kind of interested in everybody in the reaction, the reactants, the products. The rate law expresses the relationship between the reaction rate and the rate constant. And the concentration of the reactants raised to some power. So this is what a generic sort of rate law looks like here. Good luck. There we go. Like something like this. So the rate is equal to K, which once again is our rate constant that we talked a little bit about earlier. This is the concentration of A to the X power and B to the Y power. Obviously, that's the concentration like molarity. The X and the Y are what are referred to as being orders. And X is the order with respect to A. Y is the order with respect to B. And if you wanted the overall order of that reaction, you would actually just add them together. So if one was 1 and 1, the overall order would be second order for that reaction. Couple important things about the rate law. First, most important thing is what things do we do not see in the rate law? What in the reaction or equation is not in the rate law? There's no products. So rate laws are all about reactants only. So rate laws only deal with reactants. No products are in there. The other important thing is that X and Y, which are the orders, for the most part, I was going to say that, I guess so. X and Y, which are the orders, are not the coefficients in the balanced equation. So that is not how you find those guys. They're actually found experimentally. So X and Y are found experimentally, which the bad news of that is they're going to give you a table to help you find those things, but they are found experimentally only. They are not taken as the coefficients, although in some cases they can end up the same number, but that's just a coincidence. It's not how you sort of get the orders. What are the orders of the reaction? Well, you can kind of think of it as sort of like the proportion of those reactants that you need to sort of maintain a specific rate for that particular reaction. You know, kind of like when you make a dozen cookies, you got to throw in so much flour, so much, you know, chocolate chips to get a dozen cookies out. Kind of the same idea. You need to throw in the sort of the right proportions of A and B in this example here to maintain a specific rate. What is the benefit of sort of knowing the orders or figuring out the orders of a reaction? Well, you can use it to help you, you know, if you wanted to perhaps speed up a reaction or slow down a reaction, you could tell by the orders of the reaction which one maybe affects the rate more than the other. So let's just say, for example, we had a rate law that was exactly what it shows there. The rate is equal to K A times B, where each of the orders here were 1 for A and 1 for B. Right. So let's say in this reaction here, we started with, say, 2 molar of each of these guys. And we're just going to not worry about K because it's a constant. So obviously, if I did 2 times 2 here, the rate I would end up with, we'll call it 4 molar seconds or something like that. We'll add some seconds in there to make it pretty. So let's just say I wanted to know what would happen if I decided I want to double the amount of B that I'm going to start with rather than A. So in this case, I would then have the rate would equal 2 molar times, say, 4 molar if I obviously doubled it. That would then give me something like a rate that's equal to 8. So we'll call it molar per second. So in this particular rate law, or this reaction that would have this rate law, if I doubled B, I would actually double the actual rate of that reaction. It would occur twice as fast, basically, right? Now, let's say I was doing this reaction and it was like way too fast for me to record anything, right? I could also maybe decrease, right, the amount of B. Let's say I dropped it to 1 molar, right? That would then give me a rate of 2, which in that case, I just lowered the rate, slowed the reaction down by half by taking out half a B. In this particular example, you actually could do it with either reactant, right? It wouldn't make a difference which one you kind of adjusted, but you could use the knowledge of the orders and the rate law to, speed up the reaction if you needed to, slow it down, figure out what would happen if it, if you did something to it. Let's say, though, we did end up with a different rate law to start with. Let's say the rate was equal to K times A and B was, say, the second order, right? The overall rate, the overall order in this case would be what in this case? The overall order would be if A's order was 1 and B's order was 2, the overall order would be 1 plus 2 third order. Yeah. Just like over here, the overall order would be second order, right? 1 plus 1 gives us second order. Now, let's just say, for example, we started with the exact same concentrations of each of A and B as we did on the guy on the right. So if I put it in here, that would give me the rate is equal to K times 2 molar times 2 molar squared. That gives me 2 times 2 squared is 4, 4 times 2. I would end up with 8 molarity per second as my rate. Compared to our first reaction, this reaction is going to occur 4 times as fast, right? By using even the same amount of concentration of each of those, because in this case, B is second order, right? In this case, I can see what would happen if I doubled B's concentration. So if I did the same thing as I did on the other side there, that would give me 2 molar and 4 molar squared. That's a lot of math there, but that's 4 squared, which is 16. 16 times 2 is like a 32 molarity per second. I doubled the concentration of B in this reaction. The rate went up by a factor of 4. It was 4 times faster by doubling the concentration of B in this case. And it's also 4 times as fast as doubling the concentration of B in the first reaction, right? And it's like 8 times as fast as the original first reaction. The one that's the most effect on this reaction, right, if you change the concentration, would be most likely B's concentration, right? Let's say I didn't double B, but I just doubled A. If we just doubled A in the second one, it would be K times 4 times 2 squared. That would be 2 squared is 4. 4 times 4 is only 16 molar per second. So by doubling A, I could only increase the reaction twice as fast, right? But by doubling B, I can make it go 4 times as fast. So you can see the difference here. The one that's the major effect on the reaction rate in this case is actually going to be B, right? The concentration of B is going to really kind of be the one that makes the most change in the reaction rate. So this is sort of the practical application of understanding the rate law and what those orders means. It allows you to, visually, and you can figure out, to speed up the reaction, slow down the reaction. You can see which reactant maybe has a greater effect on the reaction rate than another. By the way, if I had somebody that had an order to 0 order, what does that equal? When you take something to the 0 power, it equals 1, which means, just to close on here, if I had the rate of this guy was K, A to the 0 and B squared, right, was my rate law. I could change the concentration of A as much as I like. Would it change the rate of the reaction? It wouldn't, right? So in that particular reaction, A has really no effect on the overall rate of reaction. You could change as much concentration as you want. It's all B basically that's going to be doing it. So this is really what those orders sort of allow us to understand when we look at a rate law and we see the orders, is sort of the proportion you need of each of those. And sometimes it will tell us, obviously, which one is a greater effect on the rate than the other. Any questions on that? Yeah. With the last one I just wrote, is that what you're asking? It would still be second order because it would be 2 plus 0, and you get second order. And This is how you can get a, you know, as for example, a second order reaction that has two reactants. It's also how you could get like a first order reaction that has two reactants. One could be zero order, one could be first order. The overall order would be first order and still two reactants. Other questions?